All right, welcome, Math 13 students. Tonight we're going to review for exam number 2. I'm going to do two things in our review tonight. I'm going to outline what we've done generally in each of the chapters. I'll only take a handful of minutes. And then I'm going to review the material in chapter 4. You'll see subsequent lectures where we review material in chapter 5 and in chapter 6. So follow along. What have we done? Chapter 4, that's where we began this particular set of material. This is where we introduced the notion of probability. Basically, I need you to know all those basic definitions. If you've been doing the homework, if you've been reading the problems, you cannot avoid the vocabulary. So you really need to know all those definitions. I really tried to stay away from fill in the blank questions. They don't work so well, quite honestly, in Canvas. Students are just too creative when it comes to your responses. So I tried to stay away from probability, or definitions in general. So basically, we looked at probability distributions, rules, and counting. There were no special TI-84 tools, but there were some formulas in there. Chapter 5 took a deeper dive into probability distributions. We work with probabilities. We were able to find parameters like the mean, the median, and the mean, the standard deviation, and the variance. And we were able to use probabilities to identify significant results. We looked in particular at the binomial distribution, and we used binomial PDF and binomial CDF were the two tools from the TI-84 that we used. And let's see. Chapter 6 focused on continuous probability distributions. We looked at uniform distributions, and we looked at normal distributions. In particular, we looked at the standard normal distribution, and in particular to other applications of normal distributions. We used a couple of tools to find probabilities. We used the normal CDF tool, and to find scores, we used inverse norm. So those were the TI-84 tools we used. And then we took a look at estimators. And in particular, we looked at sample and population proportions. Finally, we wrapped it up with the central limit theorem. And that's the very quick and fast outline of what we've looked at in the following chapters 4, 5, and 6 in that material. Now, what I do want to do for the balance of time tonight is focus on chapter 4, and then tomorrow night I'll do chapter 5, and then the following night chapter 6. So let me begin my review of chapter 4. That's the intro to probability. We had some very basic definitions. I'm going to throw the words out there. I'm not going to supply the definitions. You have access to the definitions in a number of different places. Oh, we had things like an event, a simple event, the compound event, the notion of a sample space. We had a couple of different ways or methods of calculating probabilities. We had the relative frequency method. That's where we count up the number of times a particular outcome occurs, and we divide it by the total number of times we engage in whatever procedure we are engaged in. There was the relative frequency method. There was the classical method. The classical method in particular required a sample space. It's one of our fundamental requirements this semester that students are able to work with simple sample spaces and calculate basic probabilities. So you'll definitely see something of that nature on the exam. There were other definitions. There were basic notions such as the notion of the complement of an event. A, and that was written, I will remind you of the notation, that was written A bar. And the probability of A bar was equal to 1 minus the probability of A. And the probability of A was 1 minus the probability of A bar. Those were plays on the fundamental notion that because A and A bar are complementary events, that is, everything not in A is going to fall into the event, the complementary event A bar. This relationship gets a lot of traction. Once we had some of those basic notions of how to count and how to round, I'll remind you, we do use 3 significant digits for probabilities. Then we got into a couple of very basic situations. We took a look at what we call the addition rule. And that was the one where we had tables of values, and we had to add them up, find a grand total. And we took a look at, well, you can look at any number of events, but we took a look at a single selection, 2 events, A and B, where you're looking at the probability of A or the probability of B. We actually need this formula for the correct calculation to occur. And this is where we would add up the probability of, say, A, whatever that number is, divided by our grand total there. There's my event B, perhaps, and doesn't happen every time, but a lot of time there's a double count, and that was the probability of A and B. It was important to remove any double count. And importantly, if A and B can not occur together in a simultaneous fashion, if it cannot happen, then the probability of A and B occurring together has got to equal 0. That means A and B are what we call disjoint or mutually exclusive. That was our addition rule. Try this one. That's our addition rule. Try that again. There we go. And a lot of times, as I say, it was important to remove this double count. Very often there is. It's where you can see a particular value had gone into one total and into a second total. You can't double count. So that was the addition rule. Then we had the multiplication rule. Very, very similar for the most part. A couple of different versions of this actually. But again, we had counts and we needed to sum to a grand total. The important thing to know about the multiplication rule is there were multiple sequential, that was the important part, events. And it really depended on how that sequence of events was happening, but the probability, A then B was really the way this usually works. The probability of A first and then B. It's important to read the questions very, very carefully because this probability of A and B, that very notation, this little bit of it anyway, appears in the addition rule. And if you're not ready for the multiple selections or events that are happen sequentially, you'll end up confused. So we needed a formula here again. The probability of A times the probability of B given A has occurred. And this little bit of detail here was the notion of independence. If the occurrence of A affects the probability of B, then A and B are dependent. If not, A and B are independent. And when A and B are independent, the probability of B given A is the same as the probability of B itself. So that means that for the multiplication rule, we essentially have two distinctly different versions of the rule depending on how the probability of B is calculated. So two events, A then B. So the probability of first A then B is equal to the probability of A times the probability of B given A has occurred, where we adjust the probability of B, assuming A has happened. And that means that, as I say, A and B are here dependent. So it's important to realize that when A and B are dependent, that's where we need to adjust the probabilities. On the other hand, sometimes I can multiply simple probabilities together directly. So in this case, this is what happens when we do not adjust the probability of B, assuming A has happened. And I'll try to explain why, and I'll run through an example. And this is what happens when A and B are independent. So again, as I say, there's an important connection in the formula between what happens with that second probability and how it's calculated. The multiplication part is straightforward. It's right there. It's a simple multiplication. It's not hard. Keeping it straight what to do, that's the real challenge. So let me run through an example of both of these. Oh, wait, one other thing before I run through an example. So the dependent case. My students usually run into the dependent case when we sample without replacement from a small population. So this is where we use the probability of B given A. As I say, I'm going to run through an example. So don't worry. That's the dependent case. Probability of B given A when we sample without replacement. The independent case, we sample with replacement. I remind you that means we take a look at our sample item, we throw it back into the pool, possibly to be sampled again. That's where I can use a straightforward probability for P of B. That's the the independent case with replacement. Straightforward probability of B. All right, so let's see. I'm going to run through an example of all of those three things. I'm going to run through the addition rule. I'm going to run through both versions of the multiplication rule just so you have an example. It's going to be a very quick, very contrived example. Then I'll end up using it again when I get to 4.3. So let's see. We have a table. I don't know, male, female, probably should be more creative, but not tonight. And I'm going to say Hartnell student or not a Hartnell student. Maybe we've done a quick survey. So male, Hartnell students, let's see, we had 9 and 3. For the female students, we had 12 and 2. So let's see, all together, we had a total of 21 Hartnell students and a total of 5 non-Hartnell students. Let's see, we had a total of 12 male and a total of 14 female. 12 and 14 are 26, 21 and 25. So there we go. So we're going to make random selections from that table. The first one, we're going to make a single selection. And in that single selection, I'm going to find the probability of selecting either a female or someone who is a Hartnell student. All right, so a couple of things here. Single selection, female or a Hartnell student. So the data I am interested in is this data here and this data here. Is there a double count? You betcha, right there. So the probability of selecting someone at random who is either female or a Hartnell student is 21 over 26. Excuse me, 14 over 26. There we go, plus 21 over 26. Minus 12 over 26. So 14 plus 21 minus 12 over 26. I need the sum of the row and the column and the grand totals. Once I run through that particular calculation, it's not particularly hard to do. You've seen me do it on many videos already. I add the numerator, find out that that's 23, and divide that by 26. So 23 over 26 is 0.885. Around it, 3 significant digits. Single selection. So I'm going to come back to the table here, and I'm going to make 2 selections. And I'm going to do the first one, excuse me, without replacement. And I'm going to look for the probability that they are both not Hartnell students. Now, I'm doing this with 2 selections without replacement. So I'm looking at the probability that the first is not a Hartnell student and the second is not a Hartnell student. So where are those students? Right here. So I'm going to be dipping into this group of 26 2 times. The first time in, there's a 5 out of 26 chance that the person selected is not a Hartnell student. Now, this is where I do this without replacement. Since I do this without replacement, when I dip back in, there's 4 out of 25. So I can plug that into my calculator exactly as we see it. 5 divided by 26 times 4 divided by 25. And I get a 0.0308. You'll notice that I reduced the grand total by 1, as well as the number of non-Hartnell students by 1. And I'm going to now do the same question. I'm going to remind you that one was without. I'm going to do the same question with replacement. So two selections, this time with replacement. So this time, I don't reduce that fraction for the second probability. It stays at 5/26 because this one was done with replacement, 5/26, because after my first selection, it went right back in to the pool there to possibly be selected again. So 5 divided by 26 times 5 divided by 26, just like it looks, and I get a 0.0370. Ooh. So that was with replacement. So you can see that we actually end up with two different probabilities. Without, that was the dependent case. With, that was the independent case. Because I did not adjust that second probability like I did up here. It was if the first event had never occurred as far as the values go in my selection. So in general, that's the way things roll. So sampling with replacement is definitely an independent case. Other things are too. Things like coin tosses. So coin tosses are independent. For example, the probability of a head, and then a head, and then a head, if you flip your coin 3 times, because my coin doesn't care what happened the first time through, I can multiply my probabilities together directly. So if it's a fair coin, it's 1/2 times 1/2 times 1/2, or 1/8, or 0.125. Now, is that number familiar? Well, yes, it is, because if you go back to the first part of chapter 4, and we take a look at the notion of a sample space, the sample space for 3 flips, head, 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 and then we take all possible combinations. It was on, I don't know which one of our, it was the chapter 4. What am I saying? Of course I'm. Well, we already did this. No. T, there we go. T, do not rush. So 3 heads, 1 out of a total of 8. There it is. It's another way to get to it using the multiplication rule. That's because my events are independent. And that's the way the multiplication rule works for multiple selections. Here it was 3 flips. Now, that takes us up through the end of 4.2. I want to take a look now at 4.3. 4.3 was a little bit of a mixed bag, in my opinion, because it really combined two, in my opinion, again, really kind of different topics. So in section 4.3, we took a look at the probability of at least one occurrence of a particular outcome. Like an example of that would be, say, flip a coin. Let's make sure it's fair. Say 5 times. We might be interested in the probability of at least one head. Now, this is the kind of thing that could be theoretically done with a sample space, somewhat similar to what I just got done looking at. But you really can't do it for anything outside of a 2 to 3 coin flips. It becomes too cumbersome to construct. So, the probability of at least one. So that means in 5 flips, that means 1 or 2 or 3 or 4 or 5 heads. That's what we really mean by at least one head. You'll notice the ors in there. That means this is an addition rule. And that's really kind of bad news for us, at least right now. We'll eventually develop a fairly sophisticated way of dealing with a broad class of problems, but not right now. So the way to approach this is to use the notion of a complement. So for example, if we're going to flip our coin, let me get a contrasted color, 5 times, and if x is equal to the number of heads, it could be 0, 1, 2, 3, 4, or 5. It could be anywhere in that range. Maybe none of them come out to be heads. Maybe all 5 in a row are heads. Unlikely, but maybe. Who knows? So what I see here is this guy right here. This is the event that I am interested in. That's my event A. That's the probability of at least one head. This is everything that is not that. So this is going to be the complementary event. That means no heads. That means they are all tails. So instead of calculating the probability of at least one head, instead we calculate one minus the probability of no heads. We're making use of that P of A equals 1 minus P of A bar, complementary event. Now, no heads means they're all tails. That's what that means. Now, what does that mean conceptually for us here? That means that my first flip was a tail, and the second flip, and the third, and the fourth, and the fifth. That means I get to multiply all those together, very much like I did in that previous example. So that's 1 minus 1/2 times 1/2 times 1/2 times 1/2 times 1/2. I'm going to squeeze it in here. That's 1 minus 1/2 raised to the 5th power. On my calculator, let me do this one. Let me do this one on my TI. Because this one, at least sometimes, can be a little bit tricky. So 1 minus. Technically, I need parentheses if I want to get the correct result in most cases. So there's my expression. There's the probability, 0.9687969. 0.969. I'll come back in just a moment. Students actually look out on this particular problem if they get the notation wrong for the just out of dumb luck. The reason they get the same result there is because this here is really 1 to the 5th. Now 1 to the 5th is always 1 anyway, so over 2 to the 5th up here, so it kind of covers its own ass there, pardon my French. In any case, there we go. So we have the probability of at least 1. Then, in addition to that, we have what we call conditional probability. And conditional probability, that's the probability of B given A. You can review my notation, but it's the probability of A and B divided by the probability of A. I do that at some point in my lecture back there in chapter 4. I'm sure it's in the office hour lectures. And that is what we call conditional probability. The big deal here is we know A has occurred. That is the condition. Like, it's a condition. A has occurred. So here's the thing about the formula. It's not a nice formula. I usually want students to consider using the intuitive rule. And that makes sense of the fact that we already know A has occurred. Now, I want to run through 2 examples of this because it does bug students sometimes. So let me go back to that data that I used before. I drew on that one pretty good. So we got some sort of random survey out there. Hey, are you a Hartnell student? Yes or no? So we had Hartnell students, non-Hartnell students. We had the men, we had the women. We had totals of 9, 12, so 21 there, 3, 2, 5 there, 12 and 14 for the genders, and then a total of 26. All right, so we want to find, after making a selection, so we're going to make a selection, we're going to find the probability of selecting, let's see, a Hartnell student given we know they are female. You got to look for this word given. It is so important. So we are focused on this problem on given. Given they are what? Female. So for this particular problem, the only people I care about are the 14 women in the poll. So the probability of selecting someone that is a Hartnell student, given they are female, how many female students are there? 14. 12 of them are Hartnell students. So 12 out of 14 is the probability. 0.857. That's the first one. Let's do another one. We're going to find the probability that they are, in this case, male, given they are not Hartnell students. That's the second one. Given they are not Hartnell students. So we're looking for the probability of selecting someone who is male, given they are not Hartnell students. So this time, the only group I care about are the non-Hartnell students. Those are the groups this is the group I care about. And out of that group, how many are male? 3 out of 5. So 3 divided by 5, 0.6. So once again, start with the given group. That's really all you care about. Then take a look at the numbers for the group of interest. In the first case, it was high school students, given they are female, 12 out of 14. And in the second case, we are looking at male, given they are not Hartnell students. In that case, it was 3 out of 5. And we have their respective probabilities, 0.857 and 0.6. And it's all down to that word given, all down to that word given. That means you get to ignore some of the data because you already know that stuff didn't occur. All right. One last section, and that's the weirdest of the group in some sense. That was 4.4. Counting. And there were four basic counting rules. There was the basic multiplication rule. Where we're looking at the number of arrangements. And that basic multiplication rule, I'll give you an example as we go through each of these, and you'll see that basic multiplication rule. Suppose we have 3 shirts. There we go. 2 different pairs of pants. 5 different pairs of shoes. How many different ways can you arrange your clothes in your closet or upon your body? So the number of arrangements there are 3 shirts times 2 pants times 5 pairs of shoes, or let's see, it looks like 30 distinct arrangements. Then there was the factorial rule. And the factorial rule, this is where we arrange n distinct objects. And that was given to us by the number, it was given by that n factorial, or it was n times n minus 1 times n minus 2, all the way down to 2 times 1. So, for example, if you have, let's see, if you have 6 books, how many different ways can you place them upon your mantle or your bookshelf? That's 6 factorial. Oh, let me run through the keystrokes here. So 6 factorial, that was 6. And to pick up the multiplication for the factorial, to pick up that funky exclamation point, we go all the way over to the almost the far right to PROB, probability. Number 4 is factorial. So this will be 6 times 5 times 4 times 3 times 2 times 1 times whang. 720 different ways. Basically, you have 6 choices for your first book, 5 for your second, 4 for your third, so on and so forth. Now, suppose we're not using all of those n objects. We have the permutation rule. That's where we select R of n distinct objects. Here, order matters. And we have some notation, NPR, and a formula, n factorial over n minus r factorial. And a quick example here would be a club with n equals 10 members, and we need to select a president and a vice president. And the question is, how many ways? Can we do that? And sometimes it is the order of things that sets the stage. And you have to think about them. What would you rather be, president or vice president? Here, the order is definitely important. So we have 10p2. So literally 10 factorial over 10 minus 2 factorial. But again, we've got this built into our calculator. So I'm going to jump over there, take care of those keystrokes. Oh, I'm sorry, I didn't stop my sharing. Let me go through that again. It's a little bit bigger now. The permutation rule, we select R of n objects. Order matters here. Sometimes in life, order matters. Just ask your younger brother. There's a formula there, but our calculator knows it. My example is the one involving a club. We've got 10 members in our club, and we need a president and a vice president. So how many different ways might we make that selection? All right, now I'm going to go ahead and share my screen. So as I say, we have 10 math back over to probability. Permutations, 10 choose 2. Hit enter. And we've got 90 different ways we might make our selection on our leadership. So 90 arrangements. All right, let me stop my share and we'll get to the very last one. We're just about out of time too. That's the permutation rule. Now we have the combination rule. And here again, we select n of r distinct objects. And order does not matter for these number of arrangements. I do not believe order matters for most lotteries. You get those numbers in any order that they show up, you're going to be a winner. So That is n choose r, and it's n factorial. Down below, we have r factorial, n minus r factorial. But again, our calculator knows the formula, and it's easy for us to get the calculator to do the work for us. So, and again, we have that club, we have 10 members. We will select 2 for cleanup committee. See, after that big party, after the big election, there's a mess. So 2 people are stuck cleaning it up. It really doesn't matter the order of those 2. They're both stuck there late cleaning stuff up. So in this case, it is 10 choose 2. And back over to my calculator. There's combinations. 10 choose 2. 45 different ways to put that cleanup committee together. So there we have it. There is my review of the the material in chapter 4. Now, in many ways, this material is truly the most intense, I think, of 4, 5, and 6. Chapter 6 has its issues, but nothing really quite like chapter 4. So the material is challenging, but you will have lots of tools. So let me go ahead and stop my recording.